So we've kind of seen how to find local extrema through the first derivative test, but there's another way to find out local extrema, and this is called the second derivative test. And so let me first just define what the second derivative test is and kind of get into some of the intricacies of it, because it's you can't use it as widely as you can use the first derivative test, and we'll see why. So the second derivative test states that if f prime of c is equal to 0 and f double prime of c is less than 0, then f has a local maximum at x equals c. And secondly, if f prime of c is equal to 0 and f double prime of c is greater than 0, then f has a local minimum at x equals c. So if we were to compare this against the first derivative test, we see that it's constrained in the fact that we can only use this test to determine local minimums and maximums if our point f prime is 0, where we know for a fact that we can have local maxes or mins when f prime of c is not even defined, right? So that's already one constraint of the second derivative test. And so whenever we have critical points that are undefined, we cannot use the second derivative test. So this can only be used when the critical point is 0. And secondly, if f double prime of c is equal to 0, then we're also kind of not able to use the second derivative test, because we can have points where the concavity, is not like concave up or concave down, but we can still have minimums and maximums. So yeah, there's really two cases where we cannot use the second derivative test, and that's where f prime of c is undefined, and where f double prime of c is either like not defined or it's either 0. And so the second derivative test is like a more constrained version of the first derivative test, but both of them allow you to find local mins and maximums if applied. And I think like another thing I want to say about the second derivative test is we kind of noticed with the first derivative test that there's a lot of cases, right? And you had to kind of test out so if we had like c, we had to see how f prime behaves on the interval around c, right? And that's not something you have to do with the second derivative test. We can simply just, if sometimes it's easier to just compute f double prime, and it's easier to find the values of f double prime of c, that's where the second derivative test is very advantageous, because we already would know f prime of c, because we kind of know we have to find out like critical points, and critical points must be where f prime of c is 0 or undefined, and so we don't have to recalculate that. And instead of looking at the behavior of f prime to the right and left of c, we can simply just plug in c into the equation for f double prime and find out its sign, and the sign alone tells us whether we have a local minimum or maximum. So at times where f double prime of c is one, easier to calculate, um, and two, it's faster to calculate than inspecting f prime around the interval c. That's where we want to really use the second derivative test. But usually the first derivative test suffices, and that's like what people mostly use to find out extreme values. But just for the sake of clarity, let us do an example of the second derivative test, and um, let's find the extreme values of the function f of x is equal to x cubed minus 12x minus 5. So f prime of x is simply 3x squared minus 12, and then f double prime of x is equal to 6x, right? Now let's find out where f prime of x is defined, and it's defined everywhere, so we can use the second derivative test for critical points. And 3x squared minus 12 is equal to 0 when x is equal to 2 or negative 2. Okay, so those are the critical points that we're worried about. And so f prime of 2 is equal to 0, f prime of negative 2 is equal to 0, and what the second derivative test tells us is that we don't have to look at the interval around 2 or negative 2 to determine whether some point is a local min or max. We just have to plug in and find the sign of f double prime at that point. So let's do that. F double prime of 2 is equal to 12, and then f double prime of negative 2 is equal to negative 12. And then the second derivative test tells us that because we have a concave up function at this point, f of 2 is a because you have a concave up function at this point, f of 2 is a local minimum. So x equals 2 is a local minimum. And then similarly, since this is concave down, and like it's really useful to just like draw out like, oh, this is what concave down looks like, and because of that we have a local maximum. So x equals negative 2 is a local maximum. And so another way you can kind of go about this is like you have f prime, right? And we know where f prime is 0 is negative 2 and 2. And previously we would query for values around the intervals. So we'd look at the sign of f prime here, here, and here. We don't have to do that anymore. The second derivative test kind of makes this case simpler, right? We just have to look at the sign of f double prime at negative 2. And at negative 2, we know that this is a negative value, and then at positive 2, we know it's a positive value. So it'll be concave up here and concave down here, and hence, because of the second derivative test, we have a local minimum at x equals 2 and a local maximum at x equals negative 2. And I think we used the same curve, and we used the first derivative test before to find its local mins and maxes, and it was kind of a bit more complex and we had to do a bit more calculation. So in cases such as these, there's times where the second derivative test is better, and so now there's like two ways we can find out local extrema, the first or second derivative test, and it's really up to you when to decide when to use it. There's cases where one is easier than the other, but the second derivative test is also more constrained than the first derivative test is.